Thank you very much. So I was asked today to talk about this project that we have, an EPSLC funded project on uncertainty quantification in prospective and predictive patient-specific cardiac models. Okay, so this is a project for which Steve Niederer and Richard Clayton are the PIs, and it's funded by EPSLC. So I should say I'm not a cardiac modeler, I'm a statistician, and I work on uncertainty quantification, and I know pretty much zero about cardiac modelling. But I was fortunate enough to meet Richard and Steve at a uncertainty quantification conference in Lausanne, and they asked me if I'd like to be involved in their project proposal, and it was funded, and so we've been doing this now for a couple of years. We've got a couple of years more left. Okay, so this is work in progress on this. Okay, these are all the people involved. Everyone in the top row here, well, it's a subset of the people involved, sorry, I should say. Everyone in the top row here is in Sheffield, and everyone on the bottom row is at King's College, London. And most of the work I'll talk about today is done by Cesare or by Sam. Okay. So, just start to say a little bit about what the project's about, and this is kind of the bit where I risk embarrassing myself trying to describe something to do with the heart. Okay. But it's about trying to predict different types of arrhythmias. Okay. So the heart I think of as this kind of electrical mechanic pump. Okay, so there's waves of electrical energy spread over the surface of the heart, causing it to contract. Okay, when it's working properly, these waves are coordinated and everything works nicely. Okay? Arrhythmia is where something goes wrong. A particular type of arrhythmia we're interested in is atrial arrhythmia. Okay, atrial fibrillation. So this is where you get these rapid and uncoordinated electrical activations leading to poor mechanical function. So I think I've got a simulation here. So I think this is Richard's simulation. So this is a rabbit ventricle, Richard. Yeah, and you've got on here on the left you've got the electrical activation as it spreads over the surface. Okay, middle of the interior, and on the right you've got the kind of phase of singularity about which these rotating waves rotate. Okay, and while it should be a smooth kind of wave that spreads through the surface, here stuff's going wrong. And you get these interesting patterns going on. Okay. So atrial fibrillation, AF, affects about 600,000 people in the UK, and one of the ways in which it's treated is by catheter ablation. Okay. So surgeons pass a wire through the artery up your groin, and then put burn lines, essentially, how I understand it, on the surface of your heart. Okay. And this burnt material, this ablated tissue, doesn't conduct electricity, and it breaks up the electrical uncoordinated waves. At least that's the idea. Okay, so unfortunately about 40% of the patients who are treated by catheter ablation for AF go on to suffer from a different type of arrhythmia called atrial tachycardia, okay, which is a fast beating of the heart. Again, I don't understand it. So the aim of our project here is to try and predict whether a patient undergoing ablation for atrial fibrillation is going to go on to have atrial tachycardia. And if they are going to, trying to infer the what I call the re-entry pathways, where these waves are going to be. And if we can infer that, then potentially we can try and guide the surgeon to treat both in a single procedure. I keep looking at Steve and Richard this. Yeah, I can't say cringing, but it's nodding. Okay. So I saw this picture from Steve. Okay, so this is what we want to do here. We want to try and answer this question, but using complex models, data, and kind of personalising these models towards given the data we have. So cardiac modelers, you guys, or people here anyway, have lots of different physical and physiological models and mathematical models of the heart. Okay, you code these into complex computer models, then do these simulations like the ones I just showed you. Okay. But these simulations require us to put lots of information in. So they need to know the shape of, say, the atrium in this case. Okay. They need to know the tissue properties over the surface of the atrium. You know, are there any regions that are damaged? Okay. So the aim is, if we can write down these models but personalise them to get those kind of unknowns right for individuals, can we use this in the clinical decision-making process? Anyway. So our approach is to take models from the literature, okay, try and build up kind of prior distributions from the population to understand how atrial manifolds vary in shape across the population and how the tissue properties vary across the population. And then, when we have a patient, to to try and specialise these prior distributions to get posterior distributions and personalised models for particular patients. Okay. And I think some of this work can be very slow and detailed. We can do it offline. Okay. Potentially, if this is going to be used in surgery, some of this needs to be fast. So we can spend lots of time here and here, but if this is going to be used while a patient's in surgery, while they're having measurements taken, we may have to do some of these steps fast, other bits need to be slower. Okay. So as Tony said this morning, if you don't have uncertainty or predictions, they're meaningless, okay, or valueless. Okay. So the key kind of question from my point of view is how confident can we be in any predictions? I said there's lots of things we don't know. We're uncertain about those things. Can we represent those uncertainties? Can we combine them? Can we make statements with probability statements about what's going to happen? Okay. So I think I said this. We want to infer re-entry pathways, so we're going to use some sort of complex tissue simulation to do this, atrial simulation to do this, okay? And that simulation is going to encode the scientific knowledge in some way. Okay? But in order to use this simulation, we require all sorts of things we don't know, like geometry, tissue properties, fiber directions, I'm not going to talk about, okay? For individual patients. So this is our basic workflow, at least for the bit of the project I'm aware of, okay, is we're going to use things like MRI scans to build patient-specific atrial models, okay, identify damaged regions by fibrotic regions and so on. Then we're going to use these electrical physiology studies to learn electrical activation maps and conduction velocities. Then we're going to use that information in some way to try and constrain all the parameters that we need to specify in order to run a more complex model and use that more complex model to look for atrial tachycardia pathways. Okay. So where does the uncertainty come in? Well, there's uncertainty everywhere here, right? We've got a fairly noisy set of data. So I'll show you some ECGs, okay, they're noisy. They're fairly sparse, they're at a small number of locations. We don't quite know where they're recorded, okay? There's an awful large number of parameters we don't know. We're going to have to describe tissue properties everywhere in our simulation. So if we've got a simulation on a finite element mesh with 10,000 nodes, okay, 10,000 points, we've got a parameter or multiple parameters at each of those points. We're going to have to describe them in some way in order to do the simulation. Okay. We've also got quite complex simulators here. We've got kind of limited computational budget. These simulators are not cheap. Okay. We can only do a certain amount of computation. And then there's things like discrepancy and misspecification, which we've not thought about thus far. Okay. But this is the kind of structure that we're trying to use. Okay. So there's some event we're interested in, so whether atrial tachycardia is going to happen. Okay. And we've collected some data. What we want to do is estimate the probability of this event happening given the data we have. So where we write this down is to think about what's the probability of that event happening if we knew all these unknown things. Okay, so if we knew the parameters, the shape, and whatever else. Okay. Well, and we want to integrate out these unknowns. So to do that, we would multiply by what we believed about these parameters given the data we collected. So there's multiple bits of information here. We've got kind of population level information. So our posterior distribution, the thing in blue here, okay, information about these unknowns for a given patient is determined by kind of some prior information times what we call a likelihood function. Okay? So we're going to use some kind of population level information to describe prior distributions over how these things vary in the population at large. Okay? We're then going to use physics, the science built into these mathematical models to provide a link between these unknowns and the data we do observe. Okay? So there's the bits in green here, the bits that involve the kind of the science hard-coded into simulators. And part of this is involving computations where we have to work out individual level kind of details. So posterior distributions for these unknowns for a given patient. Okay. So I think our strategy here is to take a fairly pragmatic approach to the proof of concept type of thing, try and specify as many certainties as we can to begin with, and try and determine which ones are important. Okay. I'll come back to tigers at the end for you, Keith. Okay. So, I thought I'd mention 3 specific problems we've been thinking about. Okay? And the first 2 are kind of published or in publication. The third one is more speculative, where we're going next. Okay? So the first one is to do with the uncertain shape, and so this is work primarily done by or led by Cesare, who's in the audience somewhere, I expect. No, maybe he's not. Okay. So we've got MRI scans of the heart. Okay. By some process I don't understand, this is converted into a representation of this atrial manifold, okay? And we do it with we put a grid down. Okay. And so I just think of this as a vector of coordinates. Okay. So we've got a vector of coordinates describing the measured atrial shape here. And typically, there's a large number of these coordinates. We've got a mesh with about 30,000 points on, so 3 coordinates each, so about 10 to the 5 different numbers here. Okay. And we know that our observation is not the truth, so we've got some kind of error model. So one of the kind of problems we face time and time again is we want to represent uncertainty in this mesh, but we need to do it parsimoniously. Okay? I can't represent uncertainty in 10 to the 5 dimensions. Okay? We don't have enough time, computer power, data to characterize uncertainty in that space. Okay? So what we're going to do is use a lower representation, dimensional representation of it. Okay? So just to make clear what that is, let's think about how we're representing x here. We're representing it in what's called the standard basis, the Euclidean basis. Right? We're just saying there's a vector in this direction, okay, a 1 and lots of zeros, okay, and there's a coefficient of that. Okay. Then there's a vector in this direction, okay, but in 10,000 dimensional space. Okay, so it's a standard basis. So we've got 10,000 or 100,000 numbers describing this thing. So what we do is very like Andrew McCulloch's talk on Wednesday. Okay, we're going to change into a basis, a lower dimensional basis that hopefully will allow us to describe this uncertainty more parsimoniously, or with fewer degrees of freedom. Okay. So we're going to change to a different basis with these orthonormal basis vectors u1 to ud. Okay? And now we're going to represent x in this new space. It's just a linear combination of this smaller number of basis vectors. Okay? So our coordinate was x, now it becomes these lambdas, just these d numbers control things in. And d, lowercase d, is the space of our new coordinates, is going to be much lower dimensional than our original space. Okay. And again, we're going to have the same split between individual kind of inference and population level inference. So we're going to use the population of measurements we have here, a large library of measurements, to estimate which basis we should use, okay, which error model we should use, what an appropriate prior distribution is in this space. Okay. We're going to build up that picture from a large number of MRI measurements of different patients. Okay. We're then going to characterize the uncertainty for any given patient by conditioning on their particular observation. Okay? So we've got lambda now, which is maybe 10-dimensional, and so we're going to just work out the posterior distribution of lambda in this new space given kind of our population level information and our reduced dimensional representation. So one question, which is kind of obvious in this case, but the question is, what basis should we use here? Our aim is to represent the distribution over shapes in a dimensional space. So just to characterize this, so this is an unsupervised problem. Yeah, there's only x here. So kind of the obvious answer here is to use a principal component basis. Okay? And this is going to change later in the talk. We're going to determine a different type of basis might be needed. Okay? So in this case, we could just let our choice of these basis vectors be the first d eigenvectors, say, of the variance of this distribution. Okay? And we like this basis for unsupervised problems because it has lots of nice properties. So one property is that the first coordinate is the direction in the data in which the data are most variable, in which shapes are most variable. Okay? The second coordinate is the direction it's next most variable, orthogonal to the first coordinate. Okay? Or another way of thinking about PCA, I know kind of everyone's probably familiar with this, is it's the best possible rank D approximation to our data. Okay, if we've got our data matrix X, PCA gives us the best rank D approximation in the Frobenius norm, so kind of squared error. It's our best possible data compression. Okay. So PCA is good for this unsupervised problem, but in supervised problems we get to later, we probably don't want to do this, and we don't know quite what we want to do, and it's a problem I'm interested in. Okay, So this is the idea. We've taken our large data set, okay, of measurements from lots of people, lots of patients. We do PCA to find the reduced space they live in and to describe a prior distribution over shapes in that space. Okay, so we get a population of space, shapes. When a new patient comes in, we get some measurements, and that allows us to characterise the uncertainty in their atrial shape quite efficiently and with a few degrees of freedom. Okay, so in Chesure's paper, if you look at it, we then did some electrophysiology simulations, and we could do simulations that take into account the uncertainty in the shape. So there's 3 patients here. We characterised the uncertainty in the shape. We did multiple simulations for different samples from the posterior, and we get the mean activation map, I'll explain what that is in a minute, and variance in these things. So you can see that the variance, you probably can't see, the activation's of the order 90, the standard deviation's about 5, so we've got about 5% uncertainty in these values that comes from not knowing the shape properly. Okay, I'm ready for time. Okay, the next problem Sam talked about yesterday. Okay. So this was to do with interpolation of a lat. But I thought before I talked about that, I'd just kind of give an aside on Gaussian processes, and that lots of people have talked about Gaussian processes, but no one's really said what they are yet. Okay? So Gaussian processes you can just think of as models of functions. Okay? Here I've just got one input x, okay, ranges between 0 and 10, and an output y, okay? And a function is a line. Okay? So here is a collection of possible functions. So a Gaussian process is just a distribution over this space of functions. Okay? So one question is, why are statisticians seemingly obsessed with using Gaussian processes? Okay, so I thought I'd choose to answer that in kind of 2 ways, why we like working with Gaussian processes. Okay. The first, and possibly the main reason, is that this is a class of models, class of functions that's closed under various operations. Okay? So what that means is, if we have 2 Gaussian processes and we add them to each other, we still have a Gaussian process, okay? Which is a nice property to have. They're also closed under Bayesian conditioning. Okay? So you take a Gaussian process, you observe some data from it, you observe the function at some locations. Okay? Suppose you observe the function somewhere. You still end up with a Gaussian process. Okay? So they're closed under Bayesian conditioning. In other words, they're mathematically tractable under learning. Okay? They're also, I think, interestingly, closed under any kind of linear operation. Okay? So if L is a linear operator, and F is a Gaussian process, then your linear operator applied to F is also a Gaussian process, and all you do, and kind of, I'm not explaining these terms, but you just apply the linear operator to your mean function, your covariance function. Okay? So what that means is the derivative of your model is still a Gaussian process. If your model is a Gaussian process, your model of a function is a Gaussian process, you can differentiate it, and you've still got a Gaussian process. You can integrate it, it's still a Gaussian process. Okay? But also, you can incorporate more complicated physics. So a different project looking at this. Okay? So L could be a more complex differential operator. For example, you might want to have 0 divergence, so you've got incompressible flow. Okay? You can build this into your covariance function so that you're automatically modelling functions that have this physical property. Okay? I think that's something that's not being exploited enough at the moment. Okay, I'll skip this, I've run out of time. The other kind of main reason is they generalise linear regression. Okay, so they're a powerful kind of non-parametric family for representing these things. Okay, so activation, we want to, we've got waves of electrical activation, so these are the colours here as they spread through the surface of the heart. So typically, these are measured in electrophysiology studies where they put a load of cathodes on the surface of the heart and they measure electrical activation at different locations, but typically at a small, kind of finite number of locations. So what we want to do, we want to interpolate this lat map to our estimate of the local activation at each point to get a picture of what happens as the activation spreads through the entire heart. So we get data at different points here, these are colours at the points. Okay? What we'd like to be able to do is produce a map of what's happening over the entire heart. Okay? And the reason we want to do that is that the local activation time map, the LAT map, tells us something about the speed with which this wavefront is moving over the surface of the heart. Okay? And the speed with which the wave is moving is related to the tissue properties on the heart. Okay? And we need to learn those tissue properties. So what we're going to try and do is use our best guess of the activation map to inform our belief about these tissue properties. Okay. That's why we're doing interpolation here. So Tad talked about this yesterday. We've got this local activation time, which is, varies over the surface of the heart, and ideally would like to model this as a Gaussian process. But the problem with doing this is that we're working on this complex domain, on this atrial manifold. Okay? It's a non-Euclidean space. And typically, for Gaussian processes, we work in terms of Euclidean distances, and we can't do that on this complex manifold. Okay. So what we do instead is this SPDE approach, stochastic partial differential equation approach, which goes back to Whittle originally. So Whittle showed that any Gaussian, a Gaussian process with a particular type of covariance function, a term covariance function, can be represented as a stochastic partial differential equation. Okay. And once you've written it down as a stochastic partial differential equation, you can solve your Gaussian process calculations using the element, the kind of machinery of finite element methods. Okay. So that has two advantages for us. It reduces the cost, okay, but it also means that we can work on irregular domains. Now, instead of being able to describe some kind of covariance function on this complex surface, now what we have to do is to solve a PDE on a mesh on the surface. Okay, it allows us to do Gaussian process type things on this mesh. Okay, so we get results from this. We can interpolate our data. We get an estimate of the activation time everywhere, and we get uncertainties from it as well. So I'm going to skip the detail about this. Okay. Okay. Unfortunately, when we look at the random samples from this thing, if we're going to characterise uncertainty, what we find, and this is a point Sam touched on yesterday, is that the random samples don't look entirely physical. We get, I can't remember, is this first activation, Sam? This is, yeah, so the activation comes over here, but we've got waves going back and forth, okay, which is not entirely physical over here. Okay? And the reason this is breaking down in our case is because the model doesn't know it's modelling a wave. This is Peter's point in our talk yesterday. Okay? So one thing we'd like to try and fix is to build in this kind of scientific knowledge into our interpolation so that it knows it's a wave, and to do so without going to the full machinery of a complex simulation. Okay. So the final kind of problem I thought I'd touch on is where we go next. Okay, how can we go about? Thank you. How can we go to learning tissue parameters for the complex simulation? Okay. So we've got a cellular model, which is a Mitchell-Schaefer model, and it has 5 parameters in, and this is the model for a single cell. Okay. We've then got a larger electrophysiology of the model of the entire atrium, okay, which is this monodomain equation with local activation given by this simpler model at each location. So the way I think about this is we've got a simulator S, which is a black box. Okay, it takes these input parameters, theta is inputs, where theta are these 5 parameters, but we've got this at each location in space. Okay, so we've got 5 each point on this mesh. We've got 5 parameters here, 5 parameters here, 5 parameters here, and so on. So we want to characterise these tissue properties everywhere, okay, and use this simulator to improve what we're doing to try and look for these kind of re-entry waves. Our problem here is that our simulator S is very expensive. Okay, so we can evaluate it at a number of points. Okay, so we can try different combinations of tissue parameter values, okay, and run the simulator to see what happens, but we can only do this at a limited number of points. Okay. So what we want to do is build an emulator here to kind of learn this representation of this mapping from our parameter space to our output space. Okay, so you've seen various talks on emulators. Okay. Unfortunately, emulation in high dimension is pretty much impossible. Okay, in very high dimensions, we can't do. Theta here is about, I can't remember, 30,000 values, something like this. Okay? We can't possibly learn do a regression in 30,000 dimensional space. In part because all points are kind of equally far apart when you get to that kind of dimension space. The way Gaussian processes work with distances just doesn't work. All points are the same distance apart, give or take. Okay. So what we're going to try and do instead is look for a lower dimensional representation of the parameter theta. So we're going to try and find a lambda, okay, which is a representation of theta, such that we can build an emulator that's a function of lambda that approximates to some quality our simulator if we were to run it at theta. Okay. The challenge is to try and find a representation here that both is detailed enough to allow us to answer questions we want to answer. Okay, so we can't reduce the dimension too much, but it's got to be of low enough dimension to allow us to build this regression space, okay, and do the inversion. Okay. So it's this trade-off between these two different kind of aspects here. So we could do the same kind of trick we talked about at the start with Cesare's work, where we use a kind of PCA type kind of expansion. So this is Carhona-Loewe expansion. So it's the same thing as PCA here. So we're just going to expand the parameter space into the directions it's most variable, the most variable direction after that, and so on. Okay. But this would be from the covariance function of our prior. Okay. Instead, we're going to try and use our lap maps instead. So we're going to use some sort of KL expansion, okay, but we're going to add in some boutique covariance functions. Okay. So we're going to use, say, the lat map we've interpolated, and maybe a fibrosis map that's estimated by other means, or maybe a conduction velocity estimate here, and try and use this to represent the spatial variability in here. And the thinking is that the heterogeneity in lat should pass into the heterogeneity in the parameter theta. Okay? And so we're going to try and reduce in this way to a lower dimensional representation. Okay, so I'll conclude. Oh, so once we've done that, sorry, we can then we're going to try and solve the inverse problem. We're going to try and learn lambda once we have some kind of forward emulator for doing this. Okay. So let's skip that. So it seems to be compulsory to quote George Box at this meeting. Okay, so in that same paper where he gave the kind of aphorism about all models wrong, but some are useless, some are useful. Sorry. It's also true that all models are wrong and plenty are useless, of course. But the same paper has this quote, so which I like more. Okay? It's inappropriate to be concerned about mice when there are tigers abroad. So the question here for us really is, where are our tigers? Okay. We know we've got this huge number of uncertain quantities, and we can't possibly hope to deal with them in that space. Okay. So we've got to find a lower dimensional representation in some way, okay, and find regularity in the problem in some way that is a low enough dimension to enable us to learn, okay, but it still allows the smoothness, the regularity in the problem. So our approach at the moment is to characterise all uncertainties and see which matter most. Okay. But then we've got the question, which uncertainties can we ignore? Okay. Which uncertainties need more degrees of freedom? When we do all these different dimension reduction approaches, how many degrees of freedom do we need for shape? How many do we need for the parameter space? How many do we need for fibrosis? Okay. Where do we need to reduce the dimension the most? Okay, thank you for listening.
Thanks a lot for the talk. How did you infer the individual variability from the shape?
What, sorry?
How do you estimate the individual variability of the shape? You have all the lambdas from the population level, you have one observation, and then you reduce that lambda, those lambdas. How do you reduce that? In my mind, once you have your PCA space, there's only one fit to that observation.
Right, so we're trying.
You estimated the distribution behind it.
Yeah, so we're trying to.
I guess there are some heuristics there, and that the heuristics are going to determine the rest of the.
That's right. So what we did, we worked out. So the idea is you work out the subspace all these things live in, okay, all these shapes live in, and then you work out the distribution over the parameters of that shape. Okay. Then when we get the then we get a new observation, we work out the distribution of our coordinates, and the reason it's a distribution, not just a single PCA projection, is because we've got the error model.
How do you get a distribution from a single point?
because we've got a prior, we've got one observation, we work out the posterior. Okay? So if you had a thing without error, so with PCA normally you don't have error, right? So you just do the projection onto that shape, and that will be out the mean of our posterior, the projection onto that point. Okay. But here we've got uncertainty about.
You have a population variability. You don't have uncertainty. You have all your population changes. I don't understand.
I think there's an error in the MRI that you're assuming that gives you a bit of wiggle room.
Yeah. So there's error in the MRI, and there's error in whatever process we've gone from. I forget the word used. The process from translating the MRI into a coordinate set of coordinates. What's it called?
Segmentation.
Segmentation, thank you, I thought it was. And so Steve gave a talk on Tuesday where he showed that different cardiologists have quite a large amount of variation in how they do that. So, yeah, our measurements are not perfect, and it's that noise in the measurement that induces the uncertainty in the shape. Yeah? But standard PCA, where you had perfect measurements, there would not be uncertainty. This is probabilistic PCA, essentially.
All right, so maybe follow up.
Okay, yeah, okay. Ask Cesare, he's the expert on it.
Once again.